Swayam Prabha. Digital India. Educated India.
Today we are going to discuss the Simplex method, the basic concepts. So far we have discussed what is the linear programming and how linear programming formulation is a very important exercise. Further, today we are going to discuss the Simplex method. See, the linear programming problems can actually be solved by the graphical method, but that is limited to only small problems. Let us say 2-variable problem. Even 3-variable problems are difficult to solve because we have there, 3-dimensional graphical exercises. That makes it very difficult. So we have already seen that we need a better method, and we have already seen that one of the basic feasible solutions become the optimal solution. So how all these things can be put together into algorithm, that is actually is our simplex algorithm. The simplex algorithm originally developed by George Bernard Danzig, an American scientist, and he started from an initial canonical tableau. The algorithm moves from one basic feasible solution to another till the optimal solution is found. So here an important word is the canonical tableau. The canonical tableau in the sense in that in the table every equation will contain at least one variable. I mean one variable. That variable is there only in that particular constraint. You see, while solving a linear programming problem by the simplex algorithm, we have the original problem which we transform to an augmented problem. The augmented problem has to be in the canonical form, and this canonical form essentially means that in the initial table, the original problem, we have the inequalities which are transformed by adding suitable slack or surplus variables to a set of equations, and in those equations at least one variable, right? One variable should be there in every equation which is unique. That means if the one variable is there only in the first equation, another variable will be there in the second, and another variable will be there in the third only. So that is called the canonical form, and every tableau should be in a canonical form in the sense that basic variables must form an unity matrix. So you see, if a variable is uniquely there in only one equation and with a coefficient of 1, so it is very clear that those basic variables will form an unity matrix. And then the powerful pivot operation is carried out, and the essential idea of the pivot operation is that a non-zero pivot element from the non-basic column is converted to 1, while the other entries in the row are converted to 0. Is it all right? So what you have to do essentially, suppose a non-basic variable becomes a basic variable. So we had one canonical form. So from one canonical form, we have to move to another canonical form. So the variable that goes out will no more be unique in one equation. Rather, the non-basic variable which now comes into the basis, that will be in only one equation, and that will be accomplished by a pivot operation, isn't it? And see that pivot operation, we require a non-zero pivot element from the non-basic column, and that is converted to 1 because it has to have an unity matrix form, while the other entries in the row are converted to 0. The variable of this column then becomes a basic variable, and the variable in the row of the pivot element becomes the non-basic variable. The choice of the pivot element is on the basis of optimality as well as feasibility consideration. So we'll explain all of these things will be very clear as we move on. So let us go ahead and try to solve a problem. See, the problem is not new. We have already taken up this problem earlier during the formulation exercises, but nevertheless, it's a quick recap. So a company produces two products, A and B. There are three resources that are required to produce the product: forming, welding, and painting. The company works for 8 hours a day. Now, if only A would have been produced, number produced would have been 90, 80, or 150 respectively from these three resources. If only B would have been produced, then number produced would have been 120, 160, or 100 respectively from the three resources. Now, if profit per unit for A and B are rupees 600 and rupees 400 respectively, find the optimal production per day of the two products so as to maximize profit. Now, as in all, product mix problem, this is also a product mix problem. So, as you see that that first resource, that is forming, if only A would have been produced, then we could have got 90. If only B would have been produced, we would have got 120. So if X1 quantity of A and X2 quantity of B are produced, then their share would be X1 by 90 and in this case X2 by 120. So essential idea is that together they should be less than equal to 1. So precisely that has been put here. Let X1 and X2 be the number produced for A and B respectively. And from these three resources we have X1 by 90 plus X2 by 120, that is less than equal to 1. That is from the first resource. X1 by 80 plus X2 by 160, that is from the second resource. And X1 by 150 plus X2 by 100, that is from the third resource. All are less than equal to 1. So in order to simplify, let us make them as multiply by 360 both sides. Then this we get 4x1 plus 3x2 less than equal to 360. Here we multiply by 160 both sides. So 2x1 plus x2 less than equal to 160. And third one, 2x1 plus 3x2 less than equal to 300. And what would be the objective function? It will be maximize z equal to 600 x1 plus 400 x2. And non-negativity constraints would be x1 greater than equal to 0 and x2 greater than equal to 0. So that would be our, the various constraints and the objective function as well as the non-negativity constraints. So the graphical solution would look like this. These are the equality constraints: 2x1 plus x2 equal to 160, 2x1 plus 3x2 equal to 300, 4x1 plus 3x2 equal to 360. So together the solution space, because they are all inequalities and they are all towards the origin. So that means O, A, B, C, D would be our solution space. So that will be solution space. The question is, where is the solution space? Is it feasible? What is the nature of the solution space? First of all, the solution space will be this side. Why? Because the constraints, they are all towards the origin, because they are all less than equal to type. And so that will be the common area. First of all, is it feasible? Yes, it's a feasible solution space because it is a bounded solution space. And also, there are corner points O, A, B, C, D, which will serve as corner point feasible solutions. And we know that one of these corner point feasible solution will be the optimal solution, because if the profit line moves parallel to itself, it will finally touch a single point before leaving the solution space. At that point, the objective function value would be the maximum. Right. So all these things we have already seen before in the linear programming knowledge. So what is the nature of the solution space? That yes, it's a convex solution space, because if we take any points within the solution space, it will be entirely within the solution space itself. All right. So this is the solution space O, A, B, C, D. It is feasible, it is bounded, and obviously it is also convex. Right. Now, these are the solutions. If we look at those points, that is 0, 0, then 80, 0, then C is 60, 40, B is 30, 80, and A is 0, 100. And if we evaluate the objective function value at the various points, then we see that the point C is our optimal solution. But you see, while graphically we begin with the origin, and then evaluate all the points and see which one is the best. We are not going to do that in a simplex. Every simplex table will represent one point, and it is usually customary to begin at the origin. That means the first solution is equivalent to the solution given by the origin. Then we move towards an optimal direction. We see in which direction we get the maximum value of the objective function. So in x1 direction, you see 600 is the profit, whereas this side is x1 direction, because this is x2 equal to 0 and this is x1 axis. So x1 values increases here, and profit is more, that is 600, whereas x2 the profit is less. But that is not the only criteria. We also have to have another criteria, that is, in order to make 1 unit of x1, how much of other units you are giving up. That means how much of these resources are you giving up, and what are the cost of those resources. That is also to be seen. Right. So before that, we have to have an augmented problem. So this is our original problem, and we create an augmented problem by adding 3 slack variables. See, because they are all less than equal to, and the problem is maximization in the standard form. So we add 3 slack variables, x3, x4, x5, and by so adding, we are getting the augmented problem. So we see that, look here is an augmented problem which has got 5 different unknowns, and there are only 3 equations. So that means only 3 can be solved. The remaining 2 has to be put to zeros. Now initially x3, x4, x5, can you see that they form a canonical form, and that means together they are having an unity matrix. So these x3, x4, x5 are called basic variables because they can be easily computed by putting the remaining variables to zeros. So see, there are 5 unknowns, only 3 can be solved, 2 are to be put to zeros, which can be called as non-basic variables. So initially the non-basic variables are x1 equal to 0 and x2 equal to 0. And x3 equal to 360, x4 equal to 160, and x5 equal to 300. That is the initial solution represented by the first table. So if this augmented problem is written in a tabular form, that first table will have x3, x4, x5 as basic variables and x1 and x2 as non-basic variables, and they are in canonical form, the basic variables, because together they form an unity matrix, and they are occurring in only one equation, and the solution of that first table is x1 0, x2 0, x3 360, x4 160, and x5 300. Now, one thing you must understand, that once you make the augmented problem out of the original problem, the augmented problem is a problem in itself. That means we need not worry where from it has come. Once it has been formed, then all the 5 variables are in the same form as far as the mathematics is concerned. Is it not? Now x3, x4, x5 are in the basis. After one or more iterations, maybe other variables will be there in the basis. Right. So let us see how this first table is obtained. So look, this is our simplex first table. So how this simplex fast table is obtained? If you look at the original problem and the augmented problem, these x3, x4, x5 are in the basis, x1, x2 are in the non-basic variables, and 360, 160, and 300 they are the variables, and the 600, 400, 0, 0, 0 they are our the profit function coefficients. Right. So you see, this is what exactly is done in the simplex fast table. There are lots of things to look into. First of all, there are bases. Basis means the variables in the basis. What are they? X3, X4, X5. So X3, X4, X5 they form the basis, and they are occurring in only one constant. That is why they are known canonical form. And these X3, X4, X5 the variables in the basis, they also form an unity matrix. So you can see that unity matrix here, is it not? So that unity matrix is formed, and the variables in the non-basis, they are not in the canonical form, and they are occurring in all the constraints, and their initial value will be 0 because they are not in the basis. So they can come into the basis. Now, what are the values of the profit coefficient values of the different variables? X1 is 600, X2 is 400, X3 is 0, X4 is 0, and X5 is also 0. Right. So these are the CJ values, and CI values are also written there for the variables in the basis. So as you know that resources, they are not initially I mean at all times they are not having any profit coefficient values. They are not part of the objective function, so their values are 0. So when you are producing 1 unit of x1, you are giving up 4 units of x3, 2 units of x4, and 2 units of x5. That means if you make 1 unit of x1, now from x1 0, x2 0, x3 360, x4 160, x5 300, our new solution will be x1 equal to 1, x2 equal to 0, x3 will be 356, x4 will be 158, and x3 will be 298. So you see, you have given up 4 units of x3, 2 units of x4, and 2 units of x5. So there is a lost profit because of that, and that term is called ZJ. So what is ZJ? ZJ is the lost profit per unit. If we want to bring 1 unit of x1 into the basis, you give up 4 units of x3, 2 units of x4, and 2 units of x5. The cost of that is 4 into 0 plus 2 into 0 plus 2 into 0 equal to 0. So ZJ value will be 0 for x1. Similarly, for making 1 unit of x2, you give up 3 units of x3, 1 unit of x4, and 3 units of x5. So therefore, the ZJ value for x2 also will be 0. So net profit, because profit per unit for x1 is 600, and net profit CJ minus ZJ per unit would be 600. And x2 also will be then 400. Right. So now therefore you see we computed CJ minus ZJ, and this is a very important consideration for simplex thing, that we have to see what is the net profit, because it's a maximization problem, to bring 1 unit of x1 into the basis, and we find that that value is 600 for x1 and 400 for x2. So once you have that, so which one should be brought into the basis? You see, first of all, we decide which one is the entering variable. That means which variable is going to come into the basis. The choice is between the two non-basic variable x1 and x2. So it is very clear that x1 should be the choice, because that is the more profitable direction. Is it not? So x1 should come into the basis. So this is precisely that is what is written, and observe the unity matrix formed by the variables in the basis in the coefficient matrix. This is one thing that we have to see, and if because that is so, the table is in canonical form, right? So that is one thing, and the basic variables are x3, x4, x5. Non-basic variables are x1, x2, and Ci and Cj are the profit coefficients. So we have already seen that, and thereafter, we computed the Cj minus Zj value. Zj is the cost of bringing 1 unit of non-basic variable into the basis, and that computation I have already shown you. And Cj minus Zj is the net profit for bringing 1 unit of non-basic variable into the basis. Is it all right? So that part we have seen, and since it is 600 is higher, more profitable direction is x1. So x1 will be now is the entering variable. That means x1 will now come into the basis. See, initially total profit equal to 0 because x1 was 0, x2 equal to 0. So total profit was 0. That means the origin was represented by the first table. So now we have found the entering variable. Because Cj minus Zj is maximum for the non-basic variable, it is also positive for a maximization problem. So hence x1 is the entering variable in the basis, and Cj minus Zj is the net profit for bringing 1 unit of non-basic variable into the basis. So I hope up to this point you have absolutely no issue and you could understand that why x1 is entering variable. Now the question is that which one should be our leaving variable? Please remember, to make 1 unit of x1, we need 4 unit of x3, 2 unit of x4 and 2 unit of x5. And the resources are available in the quantities 360, 160 and 300. So here you see this is called the feasibility consideration. So first we had taken the optimality consideration. Using that we have taken x1 as the entering variable. But now we are looking at the feasibility consideration, and using the feasibility consideration we are now trying to find out the leaving variable. So which one is the bottleneck resource? So if we have 360 of x3, 160 of x4 and 300 of x5, and we need 4 unit of x3, 2 unit of x4 and 2 unit of x5 all at the same time to make 1 unit of x1, which resource is going to be exhausted first? Say for example, suppose you think it is x3. So 360 by 4, 90 units can be produced. If we produce 90 units, then we require 90 into 4, 360 of x3, 90 into 2, 180 of x4, 90 into 2, 180 of x5. Now here you see 180 of x5 is not a problem because we have 300 unit of x5. But 180 units of x4 is going to be a problem because x4 is not available at 180. X4 is available only at 160 units. So can you see that x4 is going to be our bottleneck resource? Is it not? So always remember that when it comes to the leaving variable, always you have to look at the bottleneck resource. You can mechanically do the problem by simply divide 360 by 4, 160 by 2 and 300 by 2 and see the minimum. But you see, sometimes you get confused if there are some zeros involved. Suppose this 2 is a 0 and all those things. How do I divide 160 by 0? And all those questions will come to your mind. But really speaking, it is not a simple division and taking the minimum. It is a identification of the bottleneck resource. So in this case, the bottleneck resource will be x4. So x4 is going to be our leaving variable. So that is what has been done here. That is x4 is the x1 is the entering variable. To make 1 unit of x1, we need 4 units of x2, x3, 2 units of x4 and 2 units of x5, all of them. We have available 360 units of x3, 160 units of x4 and 300 units of x5. So we can thus make minimum of 360 by 4, 160 by 2 and 300 by 2 equal to 80 units of x1 maximum. Isn't it? So that is by division, but from a bottleneck resource point of view, you can see that only 80 units of x4 can be made, and therefore x4 is going to be our leaving variable. So what we have done so far, we have seen the optimality criteria. Using that, we have found out x1 is the leaving variable, and we have also seen the feasibility criteria, and from that feasibility criteria we have found that x4 is going to be the leaving variable. Now the question is that if x1 comes into the basis and x4 goes out of the basis, so the new set of variables will be x3, x1 and x5. So x3, x1, x3, x1 and x5, in that order they should form an unity matrix. So that means we have to now transform these constraints or these equations in a slightly different way. The x1 coefficient should be now 0, 1, 0. Look here, this is called the key row and this is called the key column. So in the key row, the intersecting element, this one is called the intersecting element should be 1. And in the key row, the key column, the other item would be zeros. That means this will be transformed to 0, 1, 0. And obviously other items will be also changed in the coefficient table. So what should be done? How do I do this transformation? A very simple rule is that in the key row, divide everything by the intersecting element. So what you will get? You will get then that x1 plus 1 by 2 x2 plus 1 by 2 x4 equal to 80. Currently it is 2x1 plus x2 plus x4 equal to 160. Divide by the intersecting element, get x1 plus 1 by 2 x2 1 by 2 x4 equal to 80. In other words, x1 can be represented as 80 minus x2 by 2 minus x4 by 2. So you see that x1, if we put in the other constants and replace x1 in those cases, see x1 is represented as 80 minus x2 minus x4. 80 minus x2 by 2 minus x4 by 2. So what will happen? In the other two constants also, x1 will be replaced by x2 and x4. Now x2 was already there. Now new entry will be x4. So what will happen? In the first constant, x1 will be eliminated. In the third constant, x1 will be eliminated. And in the second constant, x2 will be x1 will be eliminated from the first and third, and x1 will be there only in the second column, second row, that is our key row. So what we get from all these, that has been put in a nutshell, that when you want to obtain the new table, the formula, first of all, the key row values will be replaced by the old values divided by the intersecting element. So this is how the key row. The key column values will be replaced by 1 in place of intersecting element and 0 in other places. And the formula to be used is new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. So once again, the new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. Now where from this formula came? So if you look at it carefully, what I said is, first of all, you divide it by the intersecting element. So, and that would put x1 equal to 160 by 2 minus x2 by 2 minus x4 by 2. What is 2? 2 is the intersecting element. So suppose when you put it here, that 4 will now become 0. So you ensure that this 4 becomes 0 because you are replacing this x1 by that equation. Now what this 3 will become? You see what this 3 will become. because we had 4 times of x1. So 4 times of x2 by 2 that has come from here, that would be actually deducted. Is it not? So these 3 will be 3 minus 4 into 1 by 2. Is it not? So that is how we get those formula. So if you look at very carefully, because you are replacing for x1 in the first constant by 160 minus x2 by 2 minus x4 by 2, so that x2 by 2 into 4, is it not? And that is x2 by into 4 by 2. So you see 1 into 4 by 2, that is what is being deducted. So this 3 will now become 3 minus 1 into 4 divided by 2. That means 3 minus 2. So new term will be 1. All right. So let us do that calculation, and by using all this formula. So this is how the formula will go. So the formula is written here once again. So this is how the key row value is. First of all, these are changed fast. See that x4 is now replaced by x1 is the first thing to do. And then these 160 has become 80 because the intersecting element is 2, and we are dividing the key row elements by the intersecting element. So this has become 80, this has become 1, this has become half, this has become 0, this has become half, and this has become 0. So that is the key row is computed. Now about the key column. The key column intersecting element has already become 1, and the other element therefore they will become 0 and 0. Right, so we have then the key row and the key column taken care of. What about the other elements? So other elements, the formula is new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. So this 360 will become how much? 360 minus 160 into 4 by 2. How much is that? 160 into 4 by 2 equal to 160 by 2 equal to 160 into 2, 320. So 360 minus 320 equal to 40. All right. And how much is this 300 will be? 300 minus 360 into, this is, sorry, 160 into 2 by 2. That means 300 minus 160. So it will become 140. Right. So we have here then 40, 80 and 140. Let us see the other elements also. How much this 3 will become? 3 minus 4 into 1 by 2. So it is 1. This 1 will be, look here, if any of the element in key row or key column is 0, then no change would be occurring. First of all, it is also very clear that x3 remains in the basis. So, it's a good idea to first of all write the canonical form. So, canonical form would be obtained. That means the unity matrix will be there by x3, x1, x5 in that order. So x3 100, x1 010 and x5 001. This we can write straight away, without any calculation. So calculation is required for the key row, for the key column, and the remaining elements. So remaining elements are 1, 2, 3, 4. So first of all, how this minus 2 has come? Because we have 0 minus 1 into 4 by 2. Is it not? So that is minus 2. So this minus 2. How this 2 we have got? This was originally 3. So 3 minus 2 into 1 by 2. So that is 2. And how we got this minus 1? Because it was 0. 0 minus 2 into 1 by 2. So minus 1. Alright, so this is how we got the simplex second table. So what is the thing about simplex second table? So this simplex second table, we have got these values, and x3, x1 and x5 are in the basis. Once again, we can compute zj's and cj minus zj. Look here, to make 1 unit of x1, we need 1 unit of x3, half unit of x1 and 2 unit of x5. What is that? So if 1 unit of x2 we are bringing into the basis, we get a profit of 400. but we also give up in terms of lost profit something. How much? 1 unit of x3, half unit of x1 and 2 units of x5. What is the cost of 1 unit of x3? 0. Cost of half unit of x1, half into 600, 300. And how much is the cost of two units of x5? 2 into 0, 0. So net value is 300. 1 into 0 plus half into 600 plus 2 into 0. So that is 300 will be the ZJ. Same thing about x4 also. So there also ZJ value would be 300. So how much is the CJ minus ZJ? In case of x2 it is 100. In case of x4 it is minus 300. So that would be our new CJ minus ZJ calculation. So before moving further, CJ minus ZJ is the net profit per unit for bringing 1 unit of x2 into the basis and 1 unit of x4 into the basis. So now tell me, which one is the more profitable, x2 or x4? So x2 will be more profitable or x4 will be more profitable? The answer is very obvious that x2 is going to be more profitable. Since x2 is more profitable, we get x2 will be our new variable that come into the basis. Is it not? x2 will be the new variable that will come into the basis. And which one will be our living variable? Which one is the bottleneck resource? x3 is the bottleneck resource, or x1 is the bottleneck resource, or x5 is the bottleneck resource? Look at these values very carefully because x2 now comes into the basis. Just think over and tell me which one is the bottleneck resource. You see, if we make, let us say, 40 units of x2, we see that x3 gets exhausted. But does x1 gets exhausted? No, because we need only 20 units, half into 40. Does x5 gets exhausted? No, 40 into 2, 80. Right? So x5 doesn't exhaust. So only x3 gets exhausted. Only 40 units therefore can be made. And in that sense, we can easily say that our bottleneck resource is going to be x3. Is it not? So that is what we already see. Now, before going further, let us look at the pivot operation concept once again. What is this pivot operation and how the pivot operation actually happened? See, this was our first table. In the first table, we had this 100, 010, 001 with regard to x3, x4, x5. So what we did, we found out the living variable. We found out the entering variable x1. We found out the living variable x4, and we found the intersecting element, which we are calling the pivot. So what we are doing, we are dividing this pivot by this entire column so that we try to transform this 422 to 010. Is it not? Because we have to now have a new canonical form in terms of x3, x1 and x5. So initially, which was 100, 010, 001 with respect to x3, x4, x5. Now we are trying to transform that to x3, x1 and x5 in such a manner that x3, x1 and x5, they will now form 00. 100, 010 and 001. So that is the new canonical form. Can you see this new canonical form in the second table? 100, 010 and 001. So this is our pivot operation. Is it not? So exactly what the simplex does to go from the first table to the second table, it actually follows a pivot operation, and through that pivot operation, it transforms the first table to the second table. Right. So thereafter, again, for the second table, we computed Zj and Cj minus Zj values. So there we see that because the more profitable direction is our x2, so x2 is going to be our entering variable. We have already seen the bottleneck resource here is x3. So x3 will be our, the leaving variable. So what would be our next set of bases x2, x1 and x5. Isn't it? So x3 actually leaves, that is the leaving variable, because that is the bottleneck resource. The simple calculation, minimum of 40 by 1, 80 by half and 140 by 2, that is 40. See, x2 is our entering variable. To make 1 unit of x2, we need 1 unit of x3, half unit of x1 and 2 unit of x5. All three resources. We have available 40 unit of x3, 80 unit of x1 and 140 unit of x5. So we can thus make a minimum of 40 by 1, 80 by half and 140 by 2, that is 40 units of x2, that is maximum. All right. So now again we have to transform these to the through using the pivot operation to the next set of tables, and we have to bring it in the canonical form. So what exactly we have to do then? That between x3 will be now replaced by x2. So x2, x1 and x5 in that order, they should now form the unity matrix. So these 1, half and 2 should be transformed to 1, 0, 0. So 1, 0, 0 with x1 0, 1, 0 and x5 0, 0, 1. Look here, that is how the for the new set of table we should be going to get the unity matrix. Is it all right? So we get the unity matrix in a new format, and we also have to use the simplex formula to really obtain that particular set of variables. So once again, we have to, for the key row, what exactly we have to do? We have to divide each item by the intersecting element. So in this case, the intersecting element is 1 only. So it is a simple operation, 40 by 1, 0 by 1, 1 by 1, 1 by 1 and minus 2 by 1 and 0 by 1. But in this case, the same row would remain. All right, the same row would remain. So this operation is not going to be difficult. This will be 40, 0, 1, 1, minus 2 and 0. Now let us look at the values. So what 80 will become? You see 80. Now another way also you can look. So what you have to see, that you see, if you make 40 units of x2, you require 40 units of x2, 40 into 2, 20 units of x1. So you need 20 units of x1 to make 40 units of x2. So 20 will be exhausted. How much will be remaining? 80 minus 2, that is 60. So look, that is also another way of interpreting this. So when you make 20 units, 40 units of x2, how many of x5 you require? 40 into 2, that is 80. And how much you had? 140. So how many will remain? It will be 160. Sorry, 140 minus 80, that is 60. So 60 units of x5 will remain. In simple formula, if you want to calculate, it should be 40 by 1, 80 minus 40 into half by 1. That is 40 into half is 20 by 1 is 20. So 80 minus 20 is 60. Then 140 minus 40 into 2 by 1. So 40 into 2 is 80. 80 by 1 is 80 and 140 minus 80 is 60. Then we have the canonical form in the sense x2, x1 and x5 should form an unity matrix in that order. So 1, 0, 0, 0, 1, 0 and 0, 0, 1. So that part will be filled up. Now the remaining part of the matrix, so these 1 and minus 2 we have already seen. So how this 0 will become? Look at the formula, new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. So that means this 0 will become 0 minus corresponding key column into corresponding key row, 1 into half, that is half, divided by 1, so that is half. So 0 minus half, it is minus half. How much this 0 will become? 0 minus 2 into 1 by 1. So that is minus 2. How much this half will become? This half will become half minus half into minus 2 by 1. So half into minus 2 is 1 and minus of minus is plus. So that means half plus 1, it is 3 by 2. And how this minus 1 will become? This minus 1, plus, minus 2 into minus 2 by 1. That means minus 1 plus 4. So this will become 3. Is it all right? So that is how we would actually get the new set of values, and new column will be also obtained. Right, so we also shall get the new table, and from that new table we can also compute the zj and cj minus zj values, because here now x1 x2 has come here. So for x1 we have to write its corresponding ci, cj in this way, ci in this way. For x1 it is 600, for x2 it is 400. That is the profit coefficients to make 1 unit of x1 and 1 unit of x2. So to make 1 unit of x3, how much of the different resources we have to give up? We have to give up 1 unit of x2 minus half units of x1 and minus 2 units of x5. So what is the cost of that? Cost is 400 into 1, 400, minus 600 into half, 300. So and 0. So 400 minus 300, that is 100. And here 3 by 2 into 600, that is 900, minus 800. So also 100. So lost profit is 100. But since there is no profit in bringing 1 unit of x3 or x4 into the basis, so net cj minus zj is minus 100 and minus 100. See, one very interesting thing to note here is that it's a maximization problem, and now we have got both the cj minus zj values as negative. So what does that mean? It means that the optimum solution is obtained, because once all the cj minus zj values are negative, that means no point bringing them into the basis. They will not improve the solution, they will only deteriorate the solution. So at this point the basic variables are x2, x1 and x5. Non-basic variables are x3 and x4. Observe the unity matrix formed by the variables in the basis in the coefficient matrix. Could you find the table is in canonical form? Note the order of the basic variable also. Right, so those are the things to be there. And now all the cj minus zj values are negative for a maximization problem. We have found the optimal solution, and that optimal solution is x1 star equal to 60, x2 star equal to 40, and z star will be 52,000. So at the third table we have got the optimum solution. Now you see there are certain other interesting things that is also we should look into. You see, this is our simplex first table. It represents the origin, because x1 equal to 0, x2 equal to 0, x3, x4, x5, they all are equal to 360, 160 and 300. Now simplex second table, this is our simplex second table. What is the second table represents? x1 equal to 80, x3 equal to 40 and x5 equal to 140. Right, what is the value of z at this point? Value of z, because x1 is equal to 80, so 80 into 60, that is 48,000. And the optimal table, that is our simplex third table, at that time the x1 is 60, x2 equal to 40 and z equal to 52,000, and both cj minus zj values are negative. That means both x3 and x4 directions the profit is not going to improve. So you see these facts, let us look at the graphical solution once again and try to understand. You see what exactly we have done. This is the simplex first table solution. That is the origin 0, 0. That is where we began. That is the first table, x1 equal to 0 and x2 equal to 0. Now from here we have come to the point D. Because if you recall, our first table, actually second table shows x1 equal to 80. X1 was found to be more profitable direction between x1 and x2, and we found that that is becoming 80, right? So what has happened afterwards? Afterwards, we have come to the point C, right? So we have come to the point C, and point C 60/40, that has also become the optimum solution. Now look here, at that point you have seen that the variables in the basis are x1, x2 and x5. Now what is x5 here basically? If you look at the augmented problem, look here, this is our augmented problem. Yeah. So if you look at augmented problem, the x5 is associated with 2x1 plus 3x2 equal to 300. So which one is 2x1 plus x2 equal to 300? Is it not? So this one, you see, that is the variable that was in the basis. So you see the why this variable is in the basis, because you see at x1 equal to 60 and x2 equal to 40, 60 into 2 is 120, 40 into 3 is 120, 240. So you see x5 equal to 60. That means this constant is not exhausted. But at the point C, which is the intersection point of the other two cross sections, both x3 and x4 are exhausted. Is it not? Both x3 and x4 are actually exhausted because these point C is the intersection of these two constant line, and x5 is not, because that constant is somewhat away. Now what we did, we tried to find out for both x3 and x4, we exploited and try to see the nearby points. Now if you look at this one, this constraint, then the nearby point is B and F. F is, however, is not feasible. B is feasible, right? B is feasible, but B doesn't return a better solution. All right. On the other hand, if I go in the other constant direction, then we either could go back to D, but we started with D only, or we can go to H, which is not a feasible solution. So you see, C is therefore is like a peak, because you see any direction you go from C, we don't get a point which is better than C. So since it's a hill with a single peak, and it is like more like a hill climbing operation, that also essentially tells that we have actually reached a peak. All right, so this is exactly what is interesting and important in case of simplex solutions. And in this third table, that Cj minus Zj values for the basic variables, they will be definitely zeros, because after all they are already in the basis. And but for the non-basic variables, if they are all negative, that means the peak has been reached, is it not? So that is the interpretation of these simplex solutions, and essentially that is all that we have actually got. All right, so we stop here, and in this particular class, what we have actually done, we have solved we have understood the simplex methodology, the basic idea of the simplex, how to make solve a problem of simplex. Obviously maximization problem in standard form, but later on we shall also see other kind of problems and try to solve them by the simplex algorithm and things of that sort. So in the next class we are going to have some more examples of this, right? So thank you very much.